talk style meetings like this that we do remotely via Zoom, and then a couple times a year, once a quarter or so, doing like an in real life meeting for folks to who live here in the Salt Lake area to connect and talk. And so in April we are doing that. So I'm really looking forward to that meeting. Those of you who are local here, which does include Abby, our speaker today, which is really fun. So we've got another meeting or two that are scheduled here in the spring. I can think one more that's available in the spring. So you can take a look at our events there. We are supported by the R Consortium, and we use the R Consortium and the R Community Code of Conduct. So I'll drop that here. And so this is a friendly and professional space, and we are really happy to be able to treat each other with the kind of professionalism and respect that we would if we were in a room together. So Andrew and I are here to moderate as folks who are organizers for this event. So we are glad that you're here and glad to be able to have a positive environment for us here in this online meeting space. And I think that's all in terms of announcements. I'm pretty sure that is it. So join us later in the spring for other events, and then if you are a Utah person within driving distance of Salt Lake City, you can join us next month for ice cream on a Tuesday afternoon, which we'll hope for some good weather that day. I'm really excited about our talk today. So our speaker today is Abby Kaplan, and Abby is a data scientist at the Salt Lake Community College, which is, for those of you who are from outside our area, is our local county, city, I don't know, community college here in the community that has like such a big impact on like how our city and county and community do. Like, so it's really, I just love that the community college like uses data and the way that it does too, because community colleges are such important drivers in our cities and communities. So before joining SLIC, she was an adjunct professor of linguistics at the University of Utah. And she has a PhD in linguistics from UC Santa Cruz back a while back. Thank you, Andrew, for dropping the link where you can see our past meetings, including lots of our other past talks. And so, Abby, thank you so much for coming. You've spoken for us before. I'm always really excited about the kinds of things you share because it's really, really practical and applicable, but also really interesting to learn about. So I'm excited for you to talk to us today about how to handle non-linear continuous predictors in the kind of regression models that we might want to talk about. So Abby, let's get you a screen shared and unmuted and all that.
All right, I am sharing my screen here. I'm going to assume this is working unless I hear otherwise.
It looks great.
Awesome. Yes. Yes. So like Julia said, I'm a data scientist at Salt Lake Community College. The name is a little bit confusing. For a long time, I was under the impression that it was a city institution, but it's actually part of the Utah system of higher education. So like the U and UVU and all that. But its service area is in the Salt Lake Valley. And it is a great place to work. We are student focused and mission focused, and I love it here. So plug for SLIC. Yeah, so today we're going to be talking about nonlinear continuous predictors in regression models. And the target audience when I do this kind of thing is usually me from a year ago, talking about the kinds of tools that I have found useful for particular modeling challenges that I face. So maybe the not the most exciting title, but tell you what, these kinds of tools have made my life so much easier. There is I have posted to my GitHub a vignette with this material plus a little bit more. There's a little bit more on there than we will be covering today, but it has all the examples we'll see, code snippets. So if you're looking, I'm not going to post these specific slides, but all of the code that you see is available on GitHub for reference for later if you find that useful. All right, so let's talk about continuous predictors when we're doing a regression model. So in classic linear regression that we all learn when we're starting out as statisticians, the kinds of predictors that are friendly and that work well are the ones that have a linear relationship to your outcome variable. So here's an example of what that might look like. This is on the horizontal axis, we have a student's high school GPA, and on the vertical axis, we have the student's GPA in college. This right here, this is fake data. The actual relationship is not quite this clean, but I wanted to show what it looks like when it is well behaved. So as you can see, we have more or less a straight line that if you increase, if your high school GPA is half a point higher, no matter what it was, we expect a more or less constant increase in your college GPA. Both of these predictors are censored between 0 and 4, and so we get kind of some distortion at the edges here. But basically, it's a straight line. And if that's the situation that you've got, you're in great shape. You don't even need to be here. You can do linear regression like you're used to, and everything's good. Similarly, sometimes you'll find that you've got a variable that appears not to have a linear relationship with the outcome, but there's some simple transformation that you can do to make things linear. So a classic example would be if you have a variable that has a skewed distribution, sometimes you can make things look nice by taking the log. So again, this is artificial data. The real relationship is not like this, but imagine that we plot students' household income on the x-axis and their GPA on the y-axis. In this example, the smoother suggests that this is very much not a linear relationship. But if we take the log of income, now it looks linear. So in other words, a doubling of your household income predicts a constant increase in GPA. All those kinds of things are very familiar and easy to work with, and they're great. The problem is that we often, and I certainly in my work often encounter situations where we get relationships like that, where there is no simple function you can apply to a student's age to get a nice linear relationship with GPA. This also is fake data, but this is fake in ways that are highly, highly realistic. So if I plotted real data, it would look very similar to this. So what's going on here? Well, the youngest students have a really high GPA. This makes sense, right? If you're 16 and you're in college, there's probably a reason for that. Students between about 19 and 21 have the lowest average GPA. And then after that, students in their mid-20s to mid-40s have a higher GPA. And after that, maybe it falls off a bit, but we don't have many students in their 50s anyway. So it's sort of a mess, and in ways that probably correspond to substantive facts about what it's like to be a student at 19 versus a student at 30, and so on. So if I want to include age in a model, well, just throwing in your raw age is not going to be helpful because being a year older is not associated with a constant change in GPA depending on where you were. So we need something else. Similarly, we're going to use age as an ongoing example, but similarly, in our work, we often encounter this with time. So here's an example where we've got dates during a fall semester, and each dot here represents one course section. And the vertical axis is what % of the students who were enrolled in that section basically logged into the course on a given day. This is Canvas, which is our LMS. That's where you log in to get your assignments and get lecture notes and stuff like that. And what we see is, again, it's kind of a funky curve. There's sort of this general downward trend that people log on less and less as the semester goes on, which is not surprising. But we've also got a big uptick right before final exams. We've got some valleys here around like Labor Day and Thanksgiving break and maybe fall break. And there's, you could handle some of this with additional predictors in your model, like you could have an indicator for is it a long weekend, stuff like that. But there's still going to be sort of irreducible complexity in the shape of this curve. So what do we do to handle data like this in a regression? So sort of a roadmap of where we're going today. We're going to review 4 different modeling strategies you might use in this kind of situation. It's actually 3 because the first one is just ordinary linear regression. And again, if you're here, that's because that's not going to work for your use case. But we're going to start talking about regular linear regression as a point of comparison for how it is that these other techniques work. So the 3 that we'll talk about are binning. We'll talk about piecewise linear regression, and we'll talk about my favorite, splines. And for each one, we're going to look at how to fit the model. So we'll have some sample R code, talk about some packages you can use to fit these things. We will talk about how do you interpret the coefficients of the model that you get. And in particular, in service of interpreting the model, we're going to talk about what it looks like to plot the marginal effects of that ill-behaved linear predictor that you're dealing with and some confidence bands around it to understand what it is that the model is saying about your data. I'm going to assume all along that you've loaded up Tidyverse and LME4. There are some other packages that will help us as we go along, and we'll introduce them as they come up. All right, and then the data set that we'll be working with, again, this is fake but realistic data aside from the names of the variables. So this is a data set of students, and for each student we have the student's planet of origin, which is a categorical predictor with 8 possible values. We have a binary predictor if the student left-handed. We have the student's major, which is a categorical predictor with many, many, many values. I threw that in because I often need to be doing hierarchical regression, and so it's helpful for me to see an example of some packages can handle that and some can. It's helpful for me to see examples in those cases. So we'll include major as a random effect when we can. And then the two that we're most interested in, the student's age in years, that's our tricky continuous predictor here. And then the outcome we're interested in is the student's GPA. And here's an example of that looks like. So here we have a student who is from Jupiter, who's right-handed, who's majoring in music recording technology, is 17 years old, and has an almost perfect GPA. A few cautions as we go along. Basically, all the code here is sort of simplified as much as possible for purposes of illustration. So there are lots of things we would want to do to make all of these models better that you would want to do if you were doing a serious analysis. So continuous predictors, generally, you're going to want to center them. I haven't done any of that here. Age, we're treating it as though it's continuous, but of course it's actually discrete in that we don't have anything more fine than years. Really any continuous predictor that you collect is going to be discrete to the level of how many decimal points you collected. For age, it mostly is fine, but between about 17 and 25, there are actually pretty, interesting differences that happen in ways that start to matter. So there's some trickiness there. Our outcome variable GPA is bounded between 0 and 4, so really we should be doing something like censored regression to handle that, but we're going to ignore that for the sake of simplicity. And basically all these models, even apart from these considerations, there are things we could do to make them a little bit better. But this is just enough to get you started so that you can go apply it to your own problems. All right, so we're going to start with linear regression and see how it goes wrong. Okay, so with linear regression, we're going to have, so we've got age. Age is the thing we want to handle. If we include it just as a simple linear predictor, then we have one predictor associated with age in our model, and it is the age. It's very simple here. And you're going to have in your fitted model one parameter associated with age, namely the coefficient of that age predictor. So it looks like this very boring graph. Here is the student's age, and then the predictor we include in the model is just the age. And the way we model the relationship between age and GPA is we have some parameter, we multiply this number by that parameter, and we get our relationship. So the result is, here are some examples of what the relationship between age and GPA might look like, depending on your data and what the model fits. So it's going to be a line. It is going to have a slope, might be positive, might be negative. The slope might be steep or shallow, but basically it's going to be a line. So if you have reason to think that the true relationship between age and GPA has something like that kind of shape, then simple linear regression is the tool you want to use. Now, we've already seen from plotting the raw data that it's unlikely that this is the actual shape. So probably our model's not going to be very good. But let's forge ahead and see what happens when we fit this. All right. So we fit our model using our regular tools. I'm using Elmore here just to simplify getting degrees of freedom and some other summary statistics for our random effect. But basically, it's what we're all familiar with from linear regression. We predict GPA from various predictors, crucially including the student's age. And when we summarize it, we get fitted parameters for all of our predictors, including the estimate for the effective age, which this model says is 0.013 or so. What does this mean? This means the model says that for every year older you are, we think your GPA will be about 0.013 higher. That interpretation is reasonably straightforward, but we're about to see some examples in later tools where it is not that straightforward. So one thing I find particularly helpful in this scenario is to look at basically the marginal effective age across the entire age span. And I've got some pseudocode here describing how this is done. There's actual code in the vignette on GitHub. But the basic idea for what we do is as follows. We're going to use simulation to estimate what the model says is the shape of the relationship between age and GPA. So the idea is, first of all, you get all the predictors besides age, and you get the average of each one in your data set. And then you're going to start adding rows to a table. You're going to run a bunch of simulations. I did 10,000 simulations. For each simulation, you're going to sample the parameters of the model. But the reason we're going to sample is because, of course, our model doesn't just have an estimate of each parameter, but it also has a region of uncertainty around that parameter, right? So this model says we think the intercept is about 2.7, but we're not entirely certain. So for each parameter, we're going to sample that value, taking into account the uncertainty around the parameter. So that we get a collection of parameter values that are close to the estimates, but also represent our uncertainty around them. Then what we do is, within each simulation, now we've got our set of sampled parameters. We iterate over all of the ages that we're interested in. For each age, we produce the predicted GPA for a student at that age by applying our sampled parameters to that age, plus the average of all the other non-age predictors. The result is, for this sampled set of parameters, what do we predict would be your GPA if you are 17 years old or what have you, and an average student in every other way? You are an average amount of left-handedness and from an average planet, and so on and so forth. And then we just, append that to our table. At the end, what we have is, for each age, we have a whole bunch of estimates of what your GPA might be, and then we just summarize over that. So we summarize for each age, what was our average guess for your predicted GPA, and then we can get a confidence interval around that. This is all very abstract, but concretely, what it lets us do is make graphs like this. So here we have, for each age, what does the model predict is the average GPA for a student at that age who is otherwise a typical student. And when we plot that compared to the raw GPAs for those ages, this is one way to start to get a sense of, what does the model say is the shape of this relationship, and do we think that's plausible? So this is something that you should combine with your other ordinary model criticism tools, right? So combine this with things like looking at the residuals for patterns and stuff like this. But this one I find really helpful because we're about to get to places where sort of the shape of this relationship is not intuitive, and it's helpful to have a sense of using your real world knowledge to say, does this seem realistic or not? In this case, the model is doing exactly what we expect a linear regression would do. It says, hey, the relationship between age and GPA is a straight line, and it's that. And we can look at this and say, well, probably not. Clearly, there is stuff going on between the ages of about 15 and 23 that this model is not handling very well. So this gives us a baseline of what linear regression can do, but can we do better? All right. First alternative we're going to talk about is bin regression. This is a very simple technique. The idea is you're going to group this continuous predictor age into a series of bins. For example, maybe I'll put all students between 18 and 22 into a bin. And within a bin, you're going to treat all those students as being the same. And then in your model, each bin, except the first one, is going to get one parameter, which is just, it's an indicator predictor for are you in that bin or not. Basically, what we've done is we've taken this categorical predictor and turned it into a continuous predictor, and then we just do the things with that discrete, we've taken the continuous predictor, turned it into a categorical predictor, and then we just treat that discrete categorical predictor the way we would any other discrete predictor in the model. There are at least two ways you can fit this. One is you can build the bins yourself and just create a new variable age bin that has the bin assignment for each student, and then you just use your ordinary model fitting tools. It's just a normal linear regression. You've just changed what the input variables are. But sometimes you might want to do this, but you might find yourself uncertain as to whether you've chosen the right bins, right? Maybe you think, I think there's some binning behavior going on here, but I'm not confident that me looking at the data saying, that looks about right, is going to get me the right bins. Why can't I ask the model, at the same time that it's fitting all the parameters to also decide where those bins go. And there is an R package called segmented that will help you with this. So we'll look at both examples. All right, so just again for comparison with linear regression, so if we bin the students in this way, if we bin the students at up to 17, 18 to 22, 23 to 40, 41 to 50, and 51 plus, then we're going to have in these indicator predictors in the model. So we're going to have one predictor that is 1 for everybody who's in the 18 to 22 bin, 0 for everybody else. We're going to have another predictor that's 1 for everybody in the 23 to 40 bin, 0 for everybody else, and so on. So again, this is just the same thing as what you do with an ordinary categorical predictor. And as with that, as is usually the case, we either want to leave out the lowest predictor or we want to omit the intercept from the model, because otherwise we'll get non-identifiability. And so then each of these predictors will be associated with a parameter, which is just you take the predictor, you multiply it by the parameter, and that's the average GPA inside that bin. And the result is that binning is going to allow you to model relationships that look like this, where inside a bin, you have a flat horizontal line because you're treating all students in that bin as the same. And then between bins, you're going to have these discontinuous jumps, which might be large, they might be small, whatever the data justifies. So again, if you think the true relationship between age and GPA has that kind of shape, then this is probably an approach you want to try. Again, having looked at the raw plot, I'm kind of skeptical that this is the right approach for this data set, but let's try it and see what happens. All right, so here I have fit a bin model. I have constructed the bins myself, so I just create a new variable called age bin that puts them into the bins mentioned on the previous slide. And then in the model, instead of using age as a predictor, I use age bin. And here we go. Now we get one fitted parameter in the model for each bin except the lowest. And again, the coefficients are pretty easy to interpret. So we have a coefficient of negative 0.55 for the 18 to 22-year-olds. This means the model predicts that students 18 to 22 have an average GPA about half a letter grade lower than the youngest students, and that students in the next age group have an average GPA about 0.26 lower than the youngest students, and so on. Again, we can do simulation to get the marginal effects, and it looks something like this. So as promised, what the model predicts is the shape of the relationship is a series of horizontal lines with discontinuous breaks between them. This looks a little better than the linear model. I'm still not loving whatever is going on over here. In particular, we have said, the binning essentially says students from 18 to 23 are all the same. But in reality, it kind of looks like what these students have in common is not that they all have the same average GPA, but rather that GPA increases a lot each year in this age range, whereas it increases only a little bit each year subsequently. So I'm not convinced that binning is exactly the right way to go, but I think it's a little better than the linear model. I forgot to mention there for creating these marginal plots, there are R packages that will do this for you. Later we'll see some examples that the packages I'm aware of kind of struggle to handle. So again, I've just created the marginal estimates here myself, but there are ways to do it such that you don't actually have to do all the simulations yourself every time. All right. Before we move on from bin regression, though, maybe the problem here is not binning. Maybe it's just that I picked bad bins, right? Maybe I picked bad breakpoints and somebody could have done it better. So let's see what the segmented package will do for us. So segmented package provides a function called stepmented. And the first argument you feed to stepmented is just an ordinary linear model with the predictors except for the one that you want to bin. According to the documentation, there are at least some functions in the segmented package that can handle hierarchical models. And I have to confess, I have not been able to get them to work. So we're going to leave that out here. At that point, I just give up and use Stan, but that's another matter. Okay, so you feed it a model that omits the thing you want to bin. The next argument to stepmented is this seg-z argument, where you give it a formula that says, here are the continuous predictors that I want to throw into bins. And then the NPSI argument, you tell it, how many breakpoints do I want? So I'm telling it, fit me 3 breakpoints, which is going to give us 4 bins. When you summarize this, what you get is, first of all, these parameters that start with U. This is the convention used by the step method function to name the parameters of the bins. So this is saying, okay, students in the second lowest bin, because remember we omit the lowest one, have an average GPA about 0.6 lower than the youngest students, and so on. It also gives you these PSI parameters, and these represent the actual locations of the breakpoints. Now you might notice that surprisingly, the estimates for all these are 0, but they have a standard error. Kind of oddly, when you do the summary function of the model, it doesn't actually give you the estimates for PSI. They just show up as 0, but they are not in fact 0, and you can get them another way. You can get them from the PSI slot on the fitted model object. So this model says we think there's a bin at about 17. We think there's one at about 19. We think there's one at about 22 and a half, and there's some uncertainty around those breakpoints. And here's what they are. So this model has not only estimated the coefficient for each bin, but it's also come up with an estimate of where the bins are. We're going to, for reasons of time, I won't go into this in too much detail, but basically the step method function will parameterize the bins a little bit differently. The upshot of it is that the math works out the same and it's all fine, but it parameterizes the predictors such that the coefficients have a cumulative interpretation. So the idea is that each coefficient is the difference between this bin and the previous bin. Instead of with the version that we were working with before, each coefficient was the difference between this bin and the lowest bin or the intercept. So just a little thing to watch out for if you're interpreting the coefficients. All right, so let's look at the marginal estimates for this model. Now, here there's something surprising. Notice that when we looked at examples of what the shape of the relationship might be, we saw we had flat lines and then sharp breaks between them at the breakpoints of the bins, right? Well, suddenly in this graph, we have curves, which is not what we were promised. What's going on with that? So the crucial thing to keep in mind here is that when the model estimated the breakpoints between the bins, there was some uncertainty around where those breakpoints were. So what these curves are showing is the underlying model, right? The true model is going to be something with those sharp breakpoints. And what these curves represent is that we're not entirely certain where that sharp transition happens. So the reason for these 16-year-olds, the reason they are, curving downward just a little bit from the 15-year-olds is that the model says there's some sharp transition at a young age, and it might happen by the time you're 16, but probably not. And so kind of when we average it out, we think our average prediction is just a teeny bit lower for the 16-year-olds. By the time you're 17, we're much more certain that you may have, gone down into that next bin. So there's a sharp transition somewhere, but we're not entirely sure where it happens. And so when we plot this, we get a curve. Related to that, you'll notice that the confidence bands around this get suddenly really big when we get into this curvy area of the model, because basically this represents, well, we think you're either probably up here, but you might be down here, and we're not sure which. So that's what's going on. All right. So the curves look kind of nice, actually, but they're not part of what the model is actually predicting. I am still not convinced, even with this model fit, that bin regression is exactly what we want for this particular data set. In general, I think putting a sharp breakpoint is justified if you have substantive reasons to think that there is something going on the ground that would contribute to a sharp transition. So, for example, for students, lots of things happen when you turn 18, right? You become a legal adult. Lots of students graduate from high school at that age. It kind of makes sense that there would be a big change right there. So I could justify, putting a sharp breakpoint at 18. And in fact, if you know that's the case, you probably don't even need to guess the location of the bin, because you have substantive knowledge to say, yeah, it's probably right there. By contrast, if we get up into like the 30 to 50 range, lots of life events happen, but they happen at very different ages for different people. And so it makes less sense to say, yes, at 41 and a half, exactly this thing will change for people. All right, so our next tool in the toolbox is going to be a little bit like bin regression in that we're going to put some sharp breakpoints. But the difference is that we're going to allow the segments of the regression between those breakpoints to have slopes. So the idea of piecewise linear regression is like with binning, you specify breakpoints, but you're going to have basically a little miniature linear regression inside of each segment between the breakpoints. And in addition, we're going to do a little bit of algebra just to make sure that those segments line up so that we don't have those discontinuous jumps that we did with bin regression. Um, each segment gets one parameter, which is just the slope of the line inside that segment. And like with before, we can fit this in two ways. One is we can pre-specify our breakpoints and we can construct the predictors that we need and just use our regular LME4 tools, and it's easy. Or again, we can use a segmented package and tell it, here's how many breakpoints I want, but I'm not sure where they are. And just like with bin regression, the package will estimate the locations of those breakpoints for us. All right. The predictors associated with age start to get a little bit less intuitive here. The basic idea is basically this is just algebra that makes sure that each segment gets its own slope and that the segments join up at the boundaries. That's all this is doing. Basic idea is that for each, bin, we might call it, like for the 17 and under, you have a predictor that increases steadily inside of that, and then max out at the highest value for anybody who's older than that. Basically, when you add all these things up, it lets you create shapes like this. So again, each predictor for age, you're going to throw all four of these things into your linear model. Each one gets a coefficient, and if you multiply these things by their coefficients, you'll get a shape that looks like one of these things. So the kinds of relationships that piecewise regression can model are ones where you do have these sharp discontinuities, but you don't have those jumps that you had in bin regression. And instead, inside each segment, you have your own slope, and it could be positive or negative. The thing can change directions, or it can, be a similar direction all the way, just with different slopes. So if you think the true relationship between age and GPA looks something like that, piecewise regression is the way to go. And this actually looks kind of promising. This looks a lot closer to what we saw in the graph of the raw data than some of the other things we've seen. So, well, if you want to specify the breakpoints yourself, then you do a little bit of algebra. You can construct your predictors, feed them into your linear model, and here we go. And so now we get a parameter for each, segment of age that we have constructed, and the interpretation is reasonably straightforward. So here we have an estimate of negative 0.3 for the students under 18, which says that for the youngest students, every year older you are, we think your GPA will be about 0.3 lower. For students from 18 to 23, our estimate is 0.05. That means the model predicts that from ages 18 to 23, every year older you are, we think your GPA will be a teeny bit higher. And then for 23 to 45, we expect it to continue to increase, but by less, and so on and so forth. And here are the marginal estimates for what that looks like. So there's still something going on here. I'm not totally satisfied here, but this looks like an improvement. This looks much more plausibly like what the true relationship between age and GPA might be. Like with before, maybe I got the transition, the breakpoints wrong, and maybe I should let the model estimate them for me. So here's what happens if we feed them into the segmented function. So this works on analogy with the step-mented function. You feed it first a simple linear model. In this case, for kind of technical reasons about how it parameterizes things, you want to include your raw predictor as one of the predictors in your linear model. And then you give it a formula that says age is the thing I want you to break up, and I want 3 breakpoints. Like before, it will give you these U variables for the parameters of the piecewise sections, and has these PSI parameters for the breakpoints, which you can't actually see the values of in the summary, but you can see in this PSI object. So in this case, the model is extremely certain that there's a breakpoint right at 18. That makes sense. It's decently thinking that there's a breakpoint at about 23, 22 to 24, something like that. And it has no idea what that last breakpoint should be, which is perhaps a reason for us to be suspicious that there's something clearly discrete going on here. Up here, I don't know, the slope changes at some point, but I don't know where. And when we plot the, this again, I'll skip this for reasons of time, but on analogy with StepMented, the way that this package parameterizes the predictors is a little bit different. It's a sort of a cumulative effect, and that just affects how you interpret the individual parameters. So this is what the marginal effects look like. So again, like with the bin regression, now we're seeing curves, not because we say the true underlying model has curves, but rather because those curves represent our uncertainty as to where the real sharp breaks are. And you'll notice that the sort of sharpness of the curve is related to our certainty about where the breakpoint should be. So with 18, the model was real sure it should be exactly there. And so we see that this is almost sort of a perfect angle right here. For the breakpoint at around 23-ish, the model was a little less certain, and so we get, more of a curvy curve. And then out here, model has no idea where to put that breakpoint, and so we get a very gentle curve out here. All right, so when I see these curves, I know that they are not part of the true model, but that doesn't look like a bad way to model the data. And so perhaps the natural next question is, maybe the relationship is a curve, and can I just model an actual curve? And the answer is yes. Our solution is splines. So a spline, the very technical definition of a spline is that it is a wiggly curve that you build by adding together some smaller curves. Particularly, there are different ways of doing splines. We're going to talk about basis splines here. When you are going to build a spline, the idea is that a spline is like a recipe where your ingredients are these smaller, simple curves, and then you add the ingredients together in different proportions to give you a curve that wiggles in the way you want. When you construct a spline, you get to set a couple of parameters. You can set the degree of the spline, which is the polynomial degree of the basis splines that are its ingredients. It's common to use cubic splines, so you would set a degree of 3. And then you get to pick the knots, and the knots basically are sort of like breakpoints, except that there's overlap. Basically, you're going to have several miniature curves that line up along the x-axis, age in this case, and you pick how many of these breakpoints there are, and also where they are. And then when you put all these things together, the number of basis splines that you get, the number of ingredients for your spline recipe, is going to be equal to the degree you picked plus the number of knots you picked. So if you have a third degree spline and you have 5 knots, you'll get 8 basis splines. And basically, rule of thumb is the more basis splines you have, the wigglier your final curve can be. So it's actually often you'll want to play around with things, because if you have not enough splines, your spline can only be, might be smoother than your data actually justifies, and you'll miss some important information. If you have too many basis splines, then either you're going to get model fitting problems, or your model's just not going to want to know what to do with all those extra parameters, and you're in trouble. So you're going to have each basis spline is going to be a predictor in your model, and we'll get a parameter. So the idea is you multiply each basis spline by its coefficient, add them together, and that's your relationship between age and the outcome. When you're fitting these, the math for constructing basis spline is actually not that hard. It's just real tedious. There is no point in doing this yourself. It's a recipe for annoyance. But the splines package has its handy BS function that you can use to make the basis splines for you. Use that; it's much easier. Basically, it's gonna return a matrix of the predictor values you want, and you just throw those into your regular LME4 function, and it's great. So that was all very abstract. Here's what this looks like in practice. So for age, if we choose a third degree spline, and I say I want 5 knots, then the basis splines they get are going to be the following things. So you can see that they kind of, the earlier ones are for ages at the younger end, and they overlap a little bit. The yellow lines here represent where I put the knots, right? And these are just evenly spaced along the age axis until we get to the later splines, which are for older ages. So again, the way you construct your final spline is the recipe is going to be something like this curve times 0.8 plus this curve times negative 0.2 plus this curve times 0.01, or whatever it is, right? And you add those together, you get a wiggly line. You don't have to space your knots evenly. You can put them anywhere you want. And one common choice is to put them at the quantiles of your data. So here's what that would look like for age. Now, suddenly, most of our knots are in this region, which is where we have the most observations. The upshot of this is that It means that in the regions where you have more data, you're allowing your spline to be wigglier because you have more observations that might justify that wiggliness or not. So here's what the basis splines would look like in that case. Um, and here is what, this is for evenly spaced knots. Here's what kinds of splines you might get out of those 8 basis splines. So again, you're going to get some kind of curve with wiggles, maybe big wiggles, maybe small wiggles. That's the kind of model you can build. And this also looks pretty promising. I mean, this one in particular looks like almost the flipped mirror image of the relationship we actually want between age and GPA. So I'm excited. Let's see what this does for us. All right, so to fit a spline regression, we're going to use this BS function, and what we feed to it is our raw observations. So this is just a vector of all the ages we observed. We tell it the degree, and then for the BS function, we can't, as I understand it, we can't specify the number of knots without also telling it where to put the knots. But instead, we can say that it has 8 degrees of freedom, right? 8 basis splines, and then it'll work backwards and say, oh, you want 5 knots, and then it'll automatically put them at the quantiles of the data, which is what I want. And so what this returns is a matrix where each row of the matrix corresponds to one observation that you fed it, and then the columns of the matrix correspond to the basis splines. So each cell is, here is the value of basis spline number 5 for a student who's 44 years old. This is going to come with some redundancy, right? If you've got 2 students who are 22 years old, their rows will look exactly the same. But the reason we have this format is that you can just then throw this matrix into your LME function, and you get predictors for all of your basis splines, which is what we want to do. So if we throw this into a linear regression as usual, now we've got parameters for all 8 of our basis splines. Okay, cool. What do we do with that? Well, this model says that to get the proper relationship between age and GPA, one of the ingredients is negative 0.8 multiplied by that thing, which is really not very easy to interpret on its own. And I don't recommend that you try, because these coefficients really mean what they mean in the context of, like, this is the whole recipe, right? Saying you have 2 cups of flour doesn't mean much unless you know what other things you're putting into your recipe. So here is where plotting the marginal estimates I find to be really helpful. So here, really what this model says is that the relationship between age and GPA is that shape in all of its gestalt glory. So there's still, I'm not totally happy with this. I think we're not handling the youngest students very well. But I think this is a promising approach, that a spline really integrated into the model is, we think there is some kind of curvature relationship between our predictor and our outcome. And with some fiddling, I think we could get this model to serve us very well. So those are basically 3 tools that you can add to your toolbox for handling predictors like age that don't line up very well, in a linear relationship with your outcomes. And the great thing about all of these is that, with the exception of the ones where you estimate the breakpoints as part of the model, they really all just reduce to ordinary linear regression. And so that means that if you use these, all your regular model criticism tools apply, right? So you can, go in and start looking at, AIC and BIC, and you can do model comparison in the ordinary way. Your whole other linear regression toolbox still works in ways that don't limit you to just having a strict linear relationship between age and outcome. So next time you encounter a situation like this, you have options. So thank you.
Awesome, Abby. Thank you so much. That was really interesting. I think my favorite part of this whole thing was those simulations you did at the beginning that make this jagged line. I was like, oh my gosh, that is so clever. Like, that is such a, I love seeing that, to kind of like give yourself an idea there. That's super interesting. So if you've got questions, you can type them in the chat, or you can use the Q&A feature also in Zoom, and we can do that. There's a really important and great question that somebody had asked, which is, how do you think about overfitting when you think about all this? So for example, you have some set of data here, right? And then you just went through like 4-ish ways of trying to trying to decide what kind of wiggly curve to fit here. So
Mm-hmm.
how do you think about checking for overfitting, for preventing overfitting when you're doing this kind of like optimization on the like feature engineering side here? Like
Mm-hmm.
how do you approach that?
Yeah. That's a great question. I think one piece of the answer is that because so many of these just reduce to ordinary linear regression, whatever tools you ordinarily use to avoid overfitting, those tools will apply here too. And so it's going to be a combination of model statistics with sort of intuition built up from long experience of, this thing looks about right or this thing looks suspicious. Plus, I think there are a couple additional things that, at least in these examples, actually, I think are really telling. So one is, um, like we saw uh, with the piecewise linear regression with breakpoints, where when we told the segmented package to try to estimate where the breakpoints were, and it was like for sure, maybe, and that to me is a sign that maybe we're asking too much of it to try to put a breakpoint there. In fact, for the bend regression, for this one, I'm actually lying here. When you actually fit this model to the sample data, it has model fitting problems and will actually refuse to return some of the summary results. Basically, it tells you we had singularity problems, it didn't work. So I actually got these summary. It's one of those cases where it like returns the model but says you really shouldn't use this model. So I actually pulled the summary numbers out in a different way, but you should not use this actual model. And when you get things like that, again, it's another sign that I think something's going on here, which makes sense, right? Because really, the bend model is not appropriate for what's going on with age. Last thing for splines, actually. So if you do splines in Stan, there's a link in the GitHub materials. There's a guy who's done a very helpful guide to how to implement splines in a Bayesian context. And what he observed is that you can actually put a prior on the parameters for the splines in such a way that it sort of penalizes too much wiggliness, and sort of built into that is it's going to be kind of conservative and will avoid a bit of overfitting in that way. So the usual answer of there are some things you can check, and some other things you can check. Yeah.
Yeah. That's
Mm-hmm.
another thing that one thing I thought about and that, like the way I like to frame it is that we all, like often we think about if you're using a like a model that has a lot of hyperparameters, like XGBoost
Mm-hmm.
or something, you're like, well,
Mm-hmm.
okay, to know about the right hyperparameters, I need to use like resampling, like cross-validation resamples or something to like,
Mm-hmm.
so I don't trick myself,
Mm-hmm.
like to use like holdout data kind of data sets. And that often when we're thinking about this kind of like feature engineering, it's like
Mm-hmm.
it's conceptually the same. It's like
Mm-hmm.
conceptually the same that
Mm-hmm.
that it is a hyperparameter of your model. And if you're like,
Mm-hmm.
how many splines should I have? Like
Mm-hmm.
conceptually, and so it belongs in the same part of your overall modeling workflow that kind
Mm-hmm.
of hyperparameter tuning would do. And so that you can use resampling depending on
Mm-hmm.
how much data you have, and like, like you can use resampling to understand both the right number and what the like how overfit are you there.
Mm-hmm.
So that's the other thing what I like to think about is that like the thing that you should be resampling to estimate is your model feature engineering plus
Mm-hmm.
your model estimation, like not just the model
Mm-hmm.
estimation, which I think
Mm-hmm.
is pretty interesting.
Mm-hmm.
Awesome. Does anybody else have a question? Anybody else have a question? Nice. So Abby, one of the things I
Mm-hmm.
want to highlight is like how how compelling this example was. And I
Mm-hmm.
every time I hear you give a talk about like the kind of tools you use and how you apply them, I'm like, oh man, what a great example to use to be able to understand how these things work.
Mm-hmm.
So kudos on that, Abby, as always.
Thanks.
Like really easy to understand what you're getting at with the examples and whatnot you use.
Thanks. I think
Um, oh,
one
go
thing
ahead.
I think that's helpful about age is that um, I can't imagine a scenario where age, whatever, no matter what your domain is, I can't imagine a scenario where age is not a pain in this way, right?
Yeah.
If you're looking at height, right? Height
Yeah.
generally increases with age, but
Yeah.
it ain't linear.
Yeah.
Any kind of human thing we know
Yeah.
varies in interesting and substantive ways over the lifespan. So,
Yeah. 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 All right. Well, I think we've got one other question here that's about, so these packages that you talked about using
hmm
for like the marginal estimates, like the
hmm
there, you mentioned that one of them, you're like, I actually couldn't get this other part to work. But what, like,
hmm
how do you feel about the packages that are available for helping you kind of get started with these kinds of approaches for, making the bins or making the like getting these various kinds of segments and whatnot.
hmm
What are some of the limitations you've run into with using them? Or is it I guess what are the pros and cons of these kinds of packages that you
hmm
have used?
Yeah, for segmented, honestly, the big one is um, just that I have not been able to get it to do multi-level models, which is
Yeah,
something that we end up needing to do a lot. And
yeah,
again, I think later versions of it should be able to work, and it's just my limitation. I haven't succeeded in doing it yet. And then I think it's also tricky because I think this is sort of an irreducible hard thing that the package has to deal with. So I don't think it's the fault of the package, author. But once you have these breakpoints in here, there's sort of another level. It's like another thing you need to learn to get the breakpoints out and figure out how to handle them.
yeah,
One reason I didn't use a different package to do the marginal estimates is that from what I could see, that package would not handle the uncertainty around the breakpoints. Right? It would just take the mean estimate of the breakpoint and so give you a piecewise thing. And so that's why I ended up doing that part myself.
yeah, yeah,
But for things like estimating where the breakpoints go, I mean, I don't know of a better way to do it. So there's the vignette on GitHub. There are ways to estimate breakpoints in Stan, which is kind of my go-to, and I like that because basically it makes everything an example of the same thing, and it's just very very handy that you just do. Basically, it has those simulations built in, and I find it very easy to work with. But in Stan, if you start trying to estimate breakpoints, essentially your parameter space blows up, and you're really really limited in how much you can do before like the universe will die before you actually finish running your model. So for situations like that, this is really really handy.
yeah, yeah, yeah. Great. One person asked, and so I'll just drop a link here about like how can you check out what's going on with segmented and like learn more about it.
Mhm.
I just dropped a link here. It looks like unfortunately this is not a package that's on GitHub, so you can dig into the code yourself, I guess, in the
Mhm.
installation like that you have locally or one of the mirrors. But it looks like I was
Okay.
actually not aware how old, but like it's actually quite an old package on CRAN. It's been around for 20
Mhm.
plus years at this
Ooh,
point,
that's older
which
than I
is,
realized. Yes.
yeah, 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 yeah. So it might be a slightly
Yeah.
old school person who runs it,
Mhm.
maybe a
Mhm.
non GitHub user, as some of those old school art people are,
Mhm.
Yeah. Awesome. Okay, well, I want to say thank you once again to Abby so much, and thank you. So somebody else just dropped the link again to your workshop or to your materials there, which